So let me apologize in advance because I'm pretty sure I mentioned in the last video that we were looking at our last type of electron arrangement when we did Lewis dot diagrams, and I was kind of telling the truth and kind of not, because the piece that we're going to look at today are called noble gas core configurations, are essentially just a slight variation on electron configurations. So I'm going to plead partial truth on that and hope that you'll forgive me. And give you some good news. Noble gas core configurations are a nice abbreviated version of an electron configuration that you'll probably find to be pretty handy in some places. And they aren't going to require you to really learn anything new necessarily, but it gives us a sort of shorthand way of doing even a shorter version of an electron configuration. So a noble gas core configuration is also known as an abbreviated configuration. And these noble gas core configurations basically look at an atom as if it were a noble gas core in its center, and then having some additional electrons added onto that core, sort of like accessories beyond the noble gas core. What this does for us is it gives us a much shorter configuration than if we wrote out the whole configuration like we've normally done, especially for some of the larger elements in terms of a great number of electrons, where you've written out electron configurations that seem to go on and on and on and have many sublevels and orbitals included in them. These noble gas core configurations give us a lot shorter version of that and help us to focus on the parts that are most important as we move forward in chemistry. And those are going to be, more and more often you'll find, the valence electrons like you see here. So this is a format that helps us emphasize the valence electrons, and that's going to be pretty important. So it's shorter than what we've done already, and it emphasizes the electrons that are most important as we move into bonding and what's coming next with some of those things related to bonding and properties of the different elements on the periodic table. So noble gas core configuration is not a brand new thing. The first thing to point out, though, is that you have to recognize where the noble gases are on the periodic table. And hopefully by now you've had a chance to be reminded about and review some of those different regions of the periodic tables, like alkali metals, halogens, transition metals, and noble gases. And that you remember that the noble gases are these elements here on the very far right edge of the periodic table in red. What we need to do for a noble gas core configuration is figure out what that noble gas core is. And so for any element in the periodic table, you want to go backwards through the periodic table to the noble gas, one of these red ones, immediately prior to the element that you're trying to study. And we're going to build on that noble gas core of electrons. So the noble gases are those 7 elements in that last 18th column or group of the periodic table, including helium, neon, argon, krypton, xenon, radon, and oganesson. Because there aren't any elements beyond oganesson, that last one there, you won't ever use oganesson as a core. Plus, oganesson is a synthetic element anyway, and so we really don't work with it as a synthetic element. It was made in the lab, and you heard about it in a video about how new elements are made, synthesized in the lab. So all the other elements, helium down through radon at least, are potentially going to be involved in writing noble gas core electron configurations. So, for example, if we looked at argon as the core, and there we spot argon, the third noble gas down in that family or group, we can take the core of argon and use it to build electron configurations in this core format for all the elements in the next period of the table. So all the elements in this next period, from potassium through krypton, all of those could be built on an argon core, an argon noble gas core. So for example, in that blue row here, the 4th period of the periodic table, in that section we have iron. Right here we have iron. And so how would we do, for example, the noble gas core for iron? Let's take a look at that as an example. So iron has a core of electrons that we can say are the same as argon. 1s2, 2s2, 2p6, 3s2, 3p6. That's argon's configuration. And we can sort of imagine that iron is being built upon that. Iron has this core within its configuration that is the same as argon's overall configuration, but then it has those additional electrons being added on at the end, these 4s2 and 3d6 electrons that go beyond the argon core. So in order to write the noble gas core configuration for an element like iron, we would abbreviate the argon core as just an argon core. So we'd represent the argon core as argon with square brackets around it. And then in addition to the argon core, in brackets, we add on 4s2 and 3d6. So it's 2 additional sublevels with electrons, or 8 additional electrons, beyond the argon core, which includes the first 18 electrons of an iron atom. You can kind of see that here. I always describe it, it's kind of like if I called up Papa Murphy's to order a pizza, and I like their pizzas a lot. If I called up a Papa Murphy's and I said, you know, what I'd really like is, I'd like to have a pizza with Canadian bacon, pineapple, jalapenos, and mushrooms. And if they said, oh, that's basically a Hawaiian with jalapenos and mushrooms. Okay, well, it's a lot faster to say a Hawaiian with jalapenos and mushrooms than it is to rattle off all the ingredients. And that gets to be more and more true the more ingredients are on my pizza. So if Papa Murphy's had a pizza that has like 9 different toppings on it, and I want all 9 of those, which they call, let's say, the mega pizza, I want all 9 of those, plus I want pineapple and mushrooms, I could say I want the mega plus pineapple and mushrooms. That's a lot faster than rattling off 11 total toppings. I just say I want the mega plus 2 more things. Well, that's kind of what we do with these noble gas cores. We describe the core, which would be like my mega pizza, and then just briefly mention the 2 additional toppings that I want on top of that. That's what these allow us to do. And notice there we always show the bracketed core. You don't just write argon and then 4s2 3d6 because iron isn't argon. If we write Ar without the square brackets, we're sort of implying that iron has argon in it or something. And it doesn't. That's not what we mean to imply by this. It has the same sort of basic core that we could define as argon and shorten up as that, but iron certainly isn't argon. Argon's a noble gas. It doesn't react. It's hard to see. It's in the air all around us. Iron certainly isn't any of those things. And so as we look at that, the core needs to be in square brackets, and then the additional electrons are added on beyond that. Okay. So that's the idea for a noble gas core. We can do that for any element on our periodic table. So let's take a look, as always, at some examples, and we'll jump over to the homework that you've got there in order to do that. Let's take a look at this page. And if you haven't found this, this is in your binder. I think it's on page 70. If you've numbered your pages, hopefully you've done that. At least this is on page 70. The elements that are on here, some of which we've already done. In fact, argon, or rather iron, we just did as our example on the slides that we were looking through together. So we've got iron kind of in the bag already. We did iron as argon in a core plus 4s2 and 3d6. And in many cases, this is a lot shorter than writing out the entire configuration. Right? Sometimes you'll find, well, it's really not that much shorter. But for the larger elements with more and more electrons, this is real handy. And again, it helps us to emphasize and focus on seeing just the valence electrons and maybe a few extras like we see with iron. So let's look at sodium. For sodium, we want to first make sure we know where it is on the periodic table. So sodium's right here. And then the noble gas prior to it is going to be neon, which is right back up here. So sodium is neon plus 1 more electron, right? So if we think about where neon is, we just come in here and come up with neon. It's a neon core, sodium is. And then what electron is this that sodium has extra right here? Well, it's in the 3, right? 1, 2, 3. It's in the 3, and then we'd call that the 3s. So it's in the 3s1 position, sodium is. It's in 3s, and it's in the first of 2 positions there. So sodium is neon with a 3s1 electron in addition to that neon core. And that's it. All right, let's look at another example. Bromine on number 3. Clear this out. Bromine is over here on the far right side of the periodic table. As we look at it, as it's a halogen, okay, so bromine is here. Again, we're not going to build on neon this time. Bromine is one of those elements in the 4th row, the 4th period of our periodic table. So like iron, it's also built on an argon core. So bromine is going to be argon-based, and then with additional electrons on top of that. Bromine will be argon. And then in addition to argon, if we go back to our periodic table, what does bromine have in addition to that argon core? It has 4s. It has 3d. That's 10 of them. And then it has 4p5 more electrons. And if you think about it in terms of totals, bromine has 35 electrons, if you check your periodic table. Argon has 18, plus 2 in the 4s, plus 3d10, plus 4p5. That would make bromine 35 electrons total. Argon's 18 plus 17 in addition. So for bromine, we go an argon core. In addition to that, we have 4s2, all the 3d sublevel filled in, and then 4p with 5 electrons for a total of 35. Okay. What about barium? We'll just do barium, and then we'll tell you what. Let's do barium, and then we'll call that good enough for let's do number 6. Gadolinium. Oh, that's a fun one. Gadolinium is down in the D block, or rather the F block, pardon me. Gadolinium, if we count across on your periodic table there, it's the 8th element Okay, 8th element across down in the 4f section. So gadolinium would be, let's see, 1, 2, 3, 4, 5, 6, 7, right here. Gadolinium. So GD, gadolinium there, is in the 4f section. And remember that sticks in right about here in our periodic table. That's where that F block sort of inserts itself right there into that gap. So what does gadolinium follow in terms of noble gases? Okay. Well, gadolinium, I'm going to switch over to blue just for a little clarity here. Gadolinium comes right in this row, which comes right after this noble gas here, right? And which one is that? We check our periodic table. That's in the position of xenon. So gadolinium is built on a xenon core. On top of xenon, it has this section, which is our 6s. And it has the 4f section. And it has the first 8 of those. Oops, pardon me. It has the first 8 of those 4f electrons. So 6s2 and 4f8 on top of a xenon core gives us gadolinium. And let's just think about totals. Gadolinium on your periodic table should show 64 electrons total. Xenon has 54, and we've added on 2 in the 6s and 8 in the 4f. That's 10 additional on top of the core, so that's 54 and 10. That makes 64. That makes it work. So we have a xenon core for gadolinium, plus we've added on the 6s2 electrons and 8 of the 4f electrons for a total of 64. Now, you might find some variations in different sources on some of these noble gas cores. You might find them changing up a little bit. It has a little bit to do with what I mentioned to you when we first started looking at the Aufbau principle and the idea that we get into that sort of zone where things are very similar in terms of energy. What I mean is the 6s sublevel, the 4f sublevel, the 5d sublevel, they all kind of overlap sort of right in this area right here, right? We have 6s to the left, we have 4f inserting right there, and then we have 5d over here. Those all sort of mix together and overlap to where the electrons are somewhat hard to predict in there. And these are all, like we talk about with Aufbau, these are all sort of up close in energy to where the electrons can seem to do things that we have a hard time explaining. And so if you find different sources claiming perhaps that this electron configuration is a little bit different, it may very well be correct. It might not quite follow our pattern. We're not going to try to account for every single little variation. That's very, very hard and nefarious to predict, if we're being real honest. So we'll stick with this. And if you come up with something that seems a little bit off, I'll take a look at it and see if maybe you've got electrons wiggling within the range that's acceptable there and try to give you credit where I can, right? What about down here in number 11? And we'll just work on number 11 together, and then I'll let you finish the rest of this page on your own. It says here, consider an ion of chlorine with a charge of -1. Now, we haven't looked at subatomic particles and charges with our electron configurations, but let's do that. What would that element, or that ion rather, have as far as its subatomic particles? Well, if it's chlorine, a chlorine, right, would normally have, according to my periodic table, 17 protons and 17 electrons. And it doesn't give us a mass number here, so we don't have any way of talking much about the neutrons, and they're not going to be important in terms of charge or electron configuration anyway, so that's okay. But we know it has 17 protons and electrons when it's an atom, but this is an ion, though, and it has a -1 charge, which means it should be negative, right? Chlorine, in some way here, must have gained an electron. And so instead of 17 electrons, in order for it to be the chlorine ion, or we might call that the chloride ion, it would have to have 18 electrons. And if it had 17 protons and 18 electrons, then that would give us that overall -1 charge that we talk about. So that's what the configuration is, that's the setup of this chlorine ion is, 17 protons and 18 electrons. Well, what would the electron configuration be for an atom, or an ion in this case, with 18 electrons? To kind of figure that out, we want to look at writing out a configuration for 18 electrons like we normally would do. And you can look to the periodic table to do that. But for 18 electrons, we would have 1s2, 2s2, we're still going to follow the Aufbau principle, 2p6, 3s2, and chlorine would normally be 3p5. If you're looking at your periodic table, or one of those little guide tables, you'll find that chlorine would normally be in the position of 3p5, but because it's gained 1 extra electron, we need to expand that out and go to 3p6. This is a chlorine ion that has gained from a place that we'll be talking about when we get to bonding. It has gained a spare electron from somewhere. It's taken it from somewhere. And so now it isn't 3p5, it's 3p6. It's gone from having 7 valence electrons to now having an 8th valence electron. And remember, we've talked about having 8 as being especially stable. Having 8 valence electrons, we call that the octet. That's a stable configuration. Let's take a look at just jump ahead for a moment, and letter C. In terms of electrons, which other element does the chlorine ion resemble? And if you look at your periodic table, you're going to probably come up with the idea that by gaining one electron here, chlorine is going to have a configuration like the element to its right, right? So this would normally be chlorine's position here at element 17, but now it's gained an electron, so now it has an 18th electron. Now that doesn't make chlorine into argon. It wouldn't suddenly magically transform and now you'd have a bottle of argon instead. In fact, here, it's going to be argon-like, but it's not going to be argon. We would say it's argon-like. And for the noble gas core configuration, what's argon's noble gas core configuration? Now remember, looking at this whole configuration that we wrote out for the ion, that is the same configuration as argon. But even argon has a noble gas core. So this is a little bit tricky, but be thinking about it. Within that configuration, right, we have a core that's 1s2, 2s2, and 2p6. And we could say that that's a neon core. Argon has a neon core. Even the noble gases are built on a core of the noble gas that comes before them. And so argon is built on neon, and then in addition it has 3s2 and 3p6. So this would be the noble gas core configuration for argon, but it would also be the noble gas core configuration for the chlorine ion with a -1 charge. So there's that noble gas core configuration. And then lastly here on question D, why would we not call the chlorine ion by the name argon? Why can't we call chlorine argon? Think about that for a minute. What makes an element, right? What makes argon atoms argon atoms? What makes chlorine atoms chlorine atoms? In the end, and go back in your notes to when we identified this, an element is not identified by the number of electrons that it has. It's not named by that. You might come up with its charge based partly on the number of electrons, but an element's identity is based sheerly on its protons. And the important part to remember then is that this chlorine ion, we didn't change that up above. The chlorine ion still has 17 protons. The chlorine ion still has just 17 protons, and that's what identifies it. In order to become argon, it would have to have gained a proton. And we aren't looking at any ways that can happen, right? Proton number is locked as far as our concerns in this class. We're not going to look at anything in terms of nuclear decay or any sort of nuclear reactions and radioactivity where we can actually change the identities in the nucleus a bit too. That's not within the scope of our class. So for our purposes in first year chemistry, proton number never changes. And so we're looking at chlorine staying chlorine no matter what. You could take away all of its electrons. It's very, very energetically difficult to do that, but if we did, it would still be chlorine. Even if you stripped away, right, all of those electrons, it would still have 17 protons. It's still chlorine. It would have a heck of a positive charge at that point, but it would still be chlorine. Right? So there are a couple of other questions on this page for you to work on in addition to the examples at the top. Take some time with those. Go through and figure out those noble gas core configurations. Keep in mind you got to have square brackets, and that no matter what, you always have to go back to the previous noble gas, not ahead to the next one, even though the next one might be much closer. You always have to work from the previous one and build on to that. That's the only way to do a noble gas core. Right? Thanks for listening, and if you have questions, let me know or see me during Saber Time, and we'll take it from there. Until I talk to you again, have a great day.